Heat is energy that changes the temperature of a substance. You add heat energy to a substance. What happens is that the temperature of that substance should increase. Temperature will rise. If you remove heat energy from the substance, the temperature of that substance should drop. What is temperature? It's what? Coldness or hotness. Okay, measurement of coldness or hotness. How hot something is or how cold it is measured by temperature. Heat is energy. The units for heat energy is the same as the unit for any energy, which is what? Joules. Okay, we'll be using the symbol Q to represent heat energy. The units for heat energy is joules. The unit for temperature is degrees Celsius. Now for our syllabus, we are only required to know degrees Celsius or Kelvin. There is also degrees Fahrenheit, Newton degrees, and so other units for temperature. But for our syllabus, degrees Celsius, which we are using. Okay, for now, just know to convert from degrees Celsius to Kelvin, from Kelvin to degrees Celsius, and that one is easy. Converting degrees to Kelvin, you just add 273. For example, if you have got a temperature 25 degrees Celsius, this, when you add your 273, gives us how much? 298 Kelvin, and 225 degrees Celsius, it's the same temperature. It's the same kind of hotness, only that it is in a different unit, and this one is also in a different unit. Okay. Heat energy, it changes the temperature of a substance. You add heat energy, the temperature will increase. You remove heat energy, the temperature drops. Okay. Now, different substances require different amounts of heat energy. Different substances. Let's say if we have water, the amount of heat energy that water requires is different from the amount of heat energy that maybe something like copper would require. Because they are different in their nature, they are different in the way the particles are compacted compared to that. Each substance requires a different amount of heat energy in order to change its temperature. Therefore, each substance will have what is known as a specific heat capacity. Specific heat capacity of a substance is basically the amount of heat energy a 1 kg substance requires. Its temperature or 1 Kelvin. The amount of heat energy a 1 kg substance requires in order to raise its temperature by 1 degree Celsius or 1 Kelvin under normal circumstances or under normal pressure. Each substance has got its own specific heat capacity. It is the amount of heat energy that a 1 kg substance requires to raise its temperature by 1 degree Celsius or by 1 Kelvin when we are asked to define what specific heat capacity is, we should make sure that this is mentioned, your 1 kg is mentioned, and the change in temperature is mentioned. Therefore, the unit for specific heat capacity is joules per kg degrees Celsius or joules per kg Kelvin, if you are using Kelvin as your unit for your temperature. It's just the amount of heat energy that a 1 kg substance requires to raise its temperature by 1 degree Celsius. Now, all these, they will be there on your page, your information page. If they say we have water, you go to that question paper. You go to that question paper, you find the specific heat capacity for water. Specific heat capacity for water, this is 4187. 4187 joules per kg degrees Celsius. Which means if I've got 1 kg of water at a certain temperature and I need to raise it by 1 degree Celsius, I will need this amount of energy, 4187. If I've got, I can erase this part. It's still right. If I've got 1 kg of water at a temperature with T1 of, let's say, 18 degrees Celsius, in order for me to raise this to go to a T2 of 19 degrees Celsius, the amount of heat energy that I need to add should be 4187. If I need to go to another, from 19 go to 20, I still need another amount of this energy. I hope that makes sense. This is only for what? 1 kg. But what if I had 2 kgs? To raise from 18 to go to 19, I need twice as much, because this is only applicable to 1 kg. So the mass also influences how much energy will be required to raise its temperature. And also how much am I changing by? If I'm raising 2 kg from 18 degrees to go to 19, I need double the amount. To go from 19 to 20, I need again double the amount. So for every 1 degree Celsius change in temperature, I'll need twice as much. Okay? Then we'll end up with this to say, if that is true, we'll say mass affects how much energy is needed, and also your change in temperature, how much change are you taking or is taking place. This affects how much energy, heat energy is required. Therefore, the amount of heat energy that is required, Q for heat energy, is the mass times the specific heat capacity of that substance times your change in temperature. Your change in temperature, which is just your T2 minus T1. In our formula page, in our exam, specific heat capacity will come out to be C if you check on your formula page. But even if you use SHC, it's still fine, and we won't penalize us for that. Then your change in temperature, this will be your T2 minus your T1. You are changing your temperature from one temperature to the other. How much are you changing by? So these 3 components, the mass, the change in temperature, and also the type of material that is used, affects how much energy that is required. So the type of material used, which is just the specific heat capacity, the mass, how many kgs of that object you have, and the change in temperature, how much you're changing by, affects the temperature. If it is water, this would be 4187. If it is another substance, let's specific heat capacity for copper, this is 390. Copper has got a specific heat capacity of 390 joules per kg degrees Celsius, which means if I've got 1 kg of copper, I will need this amount, which is far less than how much water needs. Water needs in the thousands, 4,000 187. Copper only needs as much as this. Each substance has got its own unique specific capacity. You just calculate and you get those values. I hope we are fine. No. Now, the other thing that I want to mention about water, which I did mention when we were doing that class, is that 1 liter of water is equals to 1 kg. Okay, fresh water, not sea water. 1 liter is equals to 1 kg. The reason why I'm telling you this is that they'll tell us that we have got maybe 4 liters of water at a temperature of 19 degrees Celsius. We heat this water, it goes to 50 degrees Celsius. How much energy did this amount of water, how much energy did it take in, or how much energy is required? Since they mentioned 4 liters, and we know that 1 liter is equal to 1 kg, change in temperature, which will just be 4, times 4187. You check on your information page, then your 50 minus 19. Then we get our energy in joules. 51.88. There is no comma. Okay, that is the amount of heat energy that is required. Any questions? Makes sense. Now, it is not always that we heat up something. It is not always that you are boiling water. Sometimes you let the water cool down. When you are cooling something down, your T2 will be less than your T1. You will get a negative answer when you calculate, and you happen to have a negative answer. It means the substance was losing heat energy. A positive answer, this is a positive number. Positive means it is a heat gain. A positive Q, this is heat gain. A negative Q, it is heat lost. You are losing the amount of heat energy. When you are losing heat energy, it means your initial temperature was high, your final temperature was low. It will still be T2 minus T1, but you find that your T2 is a low number, a smaller number, your T1 is a high number. You get a negative. Then heat was lost. It is not always that you'll be minusing a big number minus a small number. Sometimes you read your questions carefully. If your T1 is high, then you get a negative. It's not always in that case. Any questions on your energy, heat energy? Law of conservation of heat energy. We know law of conservation of energy. Energy cannot be created or destroyed, but can only be converted from one form to another. It's the same thing. We cannot create energy, but we can only transform it from one form to another. Now, with the law of conservation of heat energy, this one is talking about having different substances. For example, if I have got copper, 3 kg of copper at a temperature of 150 degrees Celsius, and I've got water on this end, 2 kg of water at a temperature of 20 degrees Celsius. That is a copper block. We have water in that. if I take this copper block, place it in there, the amount of heat energy that is from here will be transferred to the water. What will end up is a mixture of those two, right? The copper and the water, they are mixed up. This one with a high temperature, very hot, right? You place it in the water, this copper will cool down. But what happens to the water? The water will heat up. Okay, so you have two things. The water at a low temperature, its temperature will rise. The copper that at a high temperature, its temperature will reduce. And when they are mixed up like this, they will end up with the same final temperature. The T2 will be the same. The T2 for the copper will be the same as the T2 for the water, because now they are mixed up. What will be happening is that the energy, do we agree copper has got high energy, high heat energy, because its temperature is high. Substances with a high temperature means high heat energy. Substances with a low temperature means low heat energy. So the amount of heat energy that this copper loses, it is just given to the water. And when water receives heat energy, its temperature should rise. This one lost heat energy, its temperature should drop. So the final temperature, T2, will be somewhere in between 20 degrees and 150. The other one that was lower will increase, the other one that was high will reduce. Then they reach the same final temperature. Law of conservation of heat energy says, we'll calculate, we'll try and calculate, when two substances at different temperature, two or more, different initial temperature. When two substances at different initial temperature are mixed, they end up with the same final temperature. The heat lost by one substance is equal to the heat gained by the other. Remember what we said, heat lost is a negative, heat gain is a positive. The heat lost by the other substance is equal to the heat gain on the other. What you'll be doing is still the same calculations for heat gain or heat lost, which is this: mass times specific heat capacity times change in temperature. Now you have two substances. There is the object that is losing, the heat lost should be equal to the heat gain. On the gain, this is what you have: mass and specific heat capacity times T2 minus T1. So your job in your calculations is to identify which one is our gaining substance, which one is our losing substance. On the losing guy, on the heat loss, it will still be the same, but on this side what we shall do, the easiest way is to do our T1 minus T2. But keep in mind, this T2 and this T2 here will be the same according to what we have just said. They will have different initial temperatures, but their final temperature should be the same. Okay? So in our example, what we said was we had copper, three kgs, this is the mass, at a temperature 150 degrees Celsius. You have water on this side. How many kgs of water did we have? 2 kgs at a temperature 19 degrees Celsius. which of the two has got high heat energy? Copper has got high heat energy, right? When you mix these two up, copper will be losing, water will be gaining. So on your calculations, the water will belong to the gaining, the copper will belong to the losing. Whatever this loses goes to the water. You check the specific heat capacity for copper, which is 390 joules per kg degree Celsius. Specific heat capacity for water, which is 4187 joules per kg degree Celsius. Then we substitute this information for this side, this information for this other side. Mass times specific heat capacity . 3 kgs times 390, 150. And then we calculate for our T2. This T2 we have already said will be the same. Seven comma 1572. Like that. T2 minus 19. I hope that is making sense. You multiply this and this guy, this times that guy. Calculations, move to the top. We'll still have our 150 minus T2 is equals to 7,1572 T2. Come again, 135, 988. Do we agree? I don't have the calculator, so I'm depending on your calculations. Okay. Then you collect the like terms. T2 and T2 can add or minus. This is an equal sign. We'll bring the T2 away. Which one are we taking? This guy to the other side. Then this guy goes to the other side. Keep in mind this is still minus T2, right? This, when it comes to the other side, becomes minus 7,1572. It's a T2. This went to the other side, becomes a minus. This is also a minus 135,988. When this comes to the other side, becomes a minus 150. On this is a 1, and this is 7,30. When you minus, it becomes negative 8,1572 T2 is equals to this, and that gives us how much? Negative 14. This is 108. How much? 285,988. I hope we are together. We divide by how much? Negative 8,1572. We divide this side by negative 8,1572. This and that will cancel the negative. Our T2 is a positive and it is in degrees Celsius. 35. 35 over 0. Our temperature, it was 150, the other one was at 19 degrees. There is no way our temperature can be over 150. And there is no way our temperature can be below 19 degrees. The other one, which was at 19, it rises until it reaches 35. The other one that was at 150, it drops until they all reach 35, that much. Now, from this calculation, you put a star on it, you put some flour. From this calculation, from this formula, which will not be given to us, they can ask for any of this. They can even give you the final temperature of the two substances, then they ask you how much was the mass of the other substance. It is not always that they'll be asking us for T2. So from that point, just know that our T2 should be the same. The rest, the initial temperature may not be the same, but they can ask for any of those components. They will not give us this. I don't know what you do, memorize it. Heat loss is equal to heat gain. On the losing side, it's T1 minus T2. On the losing side. On the gain, it is what is given. They will give us this part for the gain. It's T2 minus T1. So if you are claiming, you can frame it like that. They will not give us that one.